There is a problem with Mars that nobody in the public conversation about colonization talks about with the honesty it deserves. Not the radiation, not the thin atmosphere, not the perchlorates in the soil, or the dust storms, or the bone loss, or the psychological isolation, or the 6 to 9 month transit time, or the 500-day minimum surface stay enforced by orbital mechanics. These are real problems, and they are severe, and they deserve serious treatment. But they are engineering problems. They are problems of the kind that human ingenuity has addressed before. Not identical problems, not problems with known solutions sitting ready to be implemented, but problems that fit within a recognizable category of challenges that technology and resourcefulness can, in principle, overcome, given sufficient time and investment. The terrifying problem with colonizing Mars is different in kind. It is not an engineering problem. It is not a problem that more money or more research or more clever design can solve on any near-term timescale. It is a problem that sits at the intersection of physics and biology and human physiology, and that has an answer we have been systematically avoiding acknowledging, because the answer is deeply uncomfortable for anyone who wants to believe that Mars colonization is straightforwardly possible. The problem is gravity. Not the gravity of Mars itself, 0.38 times Earth's, as an inconvenience or as an obstacle to launch, as a physiological environment, as the condition within which human bodies would need to develop, live, and, if the vision of colonization is to mean anything lasting, reproduce. The question that the public conversation about Mars almost never addresses directly is this: can a human being live their entire life in 0.38 g and remain healthy in any meaningful sense? Can a human child develop normally? Skeletal system, cardiovascular system, muscular system, neurological system, in 0.38 grams. Can a human infant be born in 0.38 grams to a mother who gestated in 0.38 grams? And the answer to every one of these questions is the same. We do not know. We have never studied human beings in 0.38 grams for any significant length of time. We have studied human beings in zero gravity on the International Space Station extensively, and the results are concerning in ways that compound over time. We have studied human beings in Earth gravity for the entirety of human history. The gap between these two data points, 0 and 1 gram, is where Mars sits, at 0.38 gram, and we have essentially no data on what human physiology does in that specific environment on the timescales relevant to colonization. This is not a gap that can be filled quickly. Filling it requires putting human beings in 0.38 gram for years and measuring what happens to them. That requires either going to Mars, which has all the other problems we mentioned, or building rotating habitats in orbit that can simulate 0.38 g, which requires large-scale space infrastructure that does not exist. Until that data exists, every claim about the viability of human colonization of Mars is built on an assumption that has not been tested and that may turn out to be wrong in ways that make the entire enterprise not just difficult, but physiologically impossible for any human being who intends to remain biologically healthy. Tonight, we're going to examine this problem with the seriousness it deserves. Not to argue that Mars colonization is impossible, but to argue that the conversation about it has been systematically incomplete, that the most difficult problem has been given less attention than the more tractable engineering challenges, and that understanding the true scale of the gravity problem is essential for thinking honestly about what Mars colonization would actually require. Before we begin, if you put this on because the night is long and you need something substantial to sit with, stay. What follows is worth the attention it asks for. Let us start with what we know about human physiology under reduced gravity, which means starting with what we know about human physiology under zero gravity, because that is where our data actually lives. The International Space Station has been continuously inhabited since November 2000. Over more than 2 decades, hundreds of astronauts from dozens of countries have lived and worked on the station for periods ranging from a few days to over a year. The medical and physiological data from these missions represents the most comprehensive data set ever collected on human physiology in a reduced gravity environment. It is detailed, it is concerning, and it is not entirely reassuring about what happens to human bodies when you remove the gravitational loading they evolved for. The most widely discussed effect is bone loss. In microgravity, human bones lose mineral density at a rate of approximately 1 to 1.5% per month from weight-bearing bones, the spine, the hips, the legs. This is several times the rate of bone loss in elderly humans on Earth with osteoporosis. The mechanism is understood. Bone is a living tissue that continuously remodels in response to mechanical loading. When the loading disappears because gravity disappears, the bone-forming cells, osteoblasts, slow down, while the bone-resorbing cells, osteoclasts, continue operating at their normal rate. The balance that normally maintains bone density is disrupted and bone is lost. Exercise mitigates this. Astronauts on the ISS spend approximately 2 hours per day exercising using specialized equipment, treadmills with harnesses that press them against the running surface, resistance machines that substitute elastic resistance for gravitational loading. This exercise substantially reduces but does not eliminate bone loss. After 6 months in zero gravity with extensive exercise, most astronauts return to Earth with measurable bone density reductions in weight-bearing bones that require months to years of rehabilitation to recover. Some astronauts do not fully recover. After a year in microgravity, the situation is worse. Scott Kelly, who spent 340 days on the ISS in a landmark long-duration mission, returned to Earth with bone density losses, cardiovascular deconditioning, vision changes, immune function changes, and cognitive alterations that required extensive rehabilitation and that were still not fully resolved at 1 year after return. His identical twin brother Mark Kelly remained on Earth as a control subject, and the comparison between the two provided unprecedented insight into the degree to which a year in microgravity changes the human body. The cardiovascular changes are as significant as the bone changes. In microgravity, the heart does not pump blood against gravity as it evolved to do. Blood redistributes toward the head, the classic puffy face of astronauts in the first days of spaceflight, and the cardiovascular system adapts to this redistribution by downsizing. The heart muscle itself becomes smaller and less efficient. The blood volume decreases. The arteries lose some of their elasticity. The autonomic regulation of blood pressure becomes less effective. Returning astronauts frequently experience orthostatic hypotension, drops in blood pressure when standing that can cause dizziness and fainting, because their cardiovascular systems have decommissioned the infrastructure for pumping blood against gravity. The vision changes. Spaceflight-associated neuroocular syndrome, SANS, are perhaps the most alarming findings of recent spaceflight medicine. Approximately 70% of astronauts on long-duration missions show measurable structural changes in their eyes and optic nerves. The optic nerve swells, the back of the eyeball flattens. Visual acuity decreases in some affected astronauts. The leading hypothesis is that the cephalad fluid shift, the redistribution of fluid toward the head in microgravity, increases intracranial pressure, which is chronically transmitted to the optic nerve and eye. Some of these changes do not reverse after return to Earth. These are the effects of zero gravity. Mars has 0.38 times Earth's gravity, more than 0, less than 1. The obvious hope is that 0.38 grams is enough, that it provides sufficient gravitational loading to prevent or substantially reduce the pathological changes that occur in zero gravity. But this hope is not based on data. It is based on the assumption that there is a threshold somewhere between 0 and 1 g, above which the physiological effects become acceptable, and that Mars sits above that threshold. This assumption may be correct, or it may not be. We genuinely do not know where the threshold is, because we have never measured human physiology at 0.38 g for any significant duration. The ISS data from zero gravity is on one side of the question. Earth physiology data is on the other. The middle, the physiological response to partial gravity on the timescale of years and decades, is unknown territory. Let us be specific about why this matters so acutely for the question of colonization, rather than just for the question of a temporary visit. A temporary Mars mission of 3 years' duration, the minimum for a round trip given orbital mechanics, is already physiologically challenging for the reasons we have outlined. Astronauts would accumulate significant radiation doses, experience months of weightlessness in transit, spend a year and a half in Martian gravity, and then face the physiological ordeal of returning to Earth's gravity after all of that. The medical unknowns are substantial, but the risks are bounded. You are dealing with adult organisms of known baseline physiology who have agreed to accept specific risks for a finite duration. Colonization is different. Colonization means people living on Mars for decades. Colonization means people having children on Mars. Colonization means those children growing up on Mars, developing from infancy through childhood and adolescence in 0.38 g. Colonization means considering whether those people will ever be able to return to Earth, and eventually whether they will want to or need to, and eventually whether their descendants will be physiologically capable of doing so. The physiology of long-term residence in 0.38 g is what matters for colonization, and it is almost entirely unknown. The physiology of human development in 0.38 grams, from conception through gestation, through infancy, through childhood, is entirely unknown. These are the data gaps that make the colonization question genuinely unanswerable with current knowledge. We are not in a position to say that Mars colonization is physiologically viable for permanent human habitation, because we have no data on whether human beings can remain healthy over decades in 0.38 g, and no data at all on whether human development proceeds normally in that environment. Let us go through what we can predict from first principles, even without direct data, what the physics and physiology suggest about each stage of human life in Martian gravity. Begin with bone development. In Earth, children, bone density and structure develop in response to the mechanical loading of 1 g. Children who grow up in 1G develop skeletons calibrated for that environment, with the bone density and the geometry and the internal trabecular architecture appropriate for a world where things weigh what they weigh on Earth. The plasticity of bone development, the degree to which the developing skeleton responds to its mechanical environment, is much greater in children than in adults. An adult astronaut who goes to Mars with a fully formed skeleton is adapting that skeleton to a different environment. A child who grows up on Mars is forming their skeleton in that environment from the start. What happens to a skeleton that forms in 0.38 G? Physics and physiology together suggest it will be different from an Earth skeleton in ways that are broadly predictable. The bones will form with lower density. There is less gravitational loading requiring structural support, so the skeleton will optimize for the actual loading it experiences rather than the loading of Earth. The geometry of weight-bearing bones will likely differ. The cross-sectional area, the cortical thickness, the trabecular architecture will all adapt to the demands of 0.38 G rather than 1 G. The resulting skeleton will be well suited to 0.38 G. It will be structurally appropriate for Mars. It will be suboptimal for Earth. How suboptimal? This is where prediction becomes genuinely uncertain. At the extreme, the skeleton might be so different from an Earth skeleton that the person with it cannot survive in Earth gravity. The structural loading of 1 G would exceed the capacity of bones designed for 0.38 G. At the less extreme end, the differences might be manageable with medication, physical therapy, supportive devices, or some combination of these. We do not know which end of this range Mars-developed skeletal physiology will fall toward, because we have no data on skeletal development at 0.38 G. The cardiovascular system tells a similar story. An Earth-developed cardiovascular system is calibrated to pump blood against 1 G. The heart muscle has the specific size and contractile force needed for this task. The vessels have the wall thickness and elasticity appropriate for the pressures involved. The autonomic regulation has the responsiveness calibrated to the dynamic range of gravitational loading that an active person on Earth experiences: standing, sitting, lying down, exercising. All of this calibration happens during development, especially during the first years of life, when the cardiovascular system is most plastic. A cardiovascular system that develops in 0.38 grams will be calibrated for a world where blood weighs less than half what it weighs on Earth. The heart will develop to be smaller, it has less work to do. The vessels will develop with different wall characteristics. The autonomic regulation will be calibrated to a narrower dynamic range of gravitational loading. This cardiovascular system will work well on Mars. It will be underpowered for Earth. Whether it will be dangerously underpowered, whether a Mars-born person visiting Earth would be at significant risk of cardiovascular failure, is unknown. The muscular system is perhaps the most immediately intuitive case. Muscles develop in response to the demands placed on them. Children developing on Earth develop musculature calibrated for carrying their body weight and moving through a 1G environment. The leg muscles, the postural muscles of the back, the core muscles that stabilize the spine. In 0.38 G, these demands are less than half what they are on Earth. A child developing in 0.38 G would develop less massive and less powerful leg and postural musculature than a child developing on Earth. Not because anything went wrong, but because the muscles optimized for the actual demands placed on them. The resulting musculature will be appropriate for Mars. It will be insufficient for Earth. The person will be effectively weak relative to what Earth gravity demands of the locomotor system. The neurological system, the vestibular system in particular, raises perhaps the most interesting questions. The vestibular system is the sensory system that detects acceleration and head position. It is the system that tells your brain which way is up, that detects your motion through space, that contributes to your sense of balance and spatial orientation. It works through fluid-filled canals and chambers in the inner ear, where tiny hair cells respond to the movement of fluid and to the position of small calcium carbonate crystals, otoliths, that settle under gravity. The otoliths settle in the direction of gravity. Their position signals to the brain which way is down. In 1G, they settle in the direction they have always settled for terrestrial organisms. In zero gravity, they do not settle consistently. This is part of why astronauts experience space sickness in the first days of weightlessness, as the vestibular system receives conflicting signals. After adaptation to microgravity, the vestibular system recalibrates. Astronauts lose their reliance on vestibular cues for orientation and rely more on visual and other cues. Returning to Earth requires recalibration again. In 0.38 G, the otoliths will settle. There is real gravity pulling them, but they will settle with less force than in 1G. The signal they send to the brain will be weaker. How the developing nervous system calibrates to this weaker signal is unknown. It seems likely that it would calibrate to 0.38 G as normal, that the brain of a Mars-born child would develop its model of which way is down based on 0.38 G rather than 1G. This calibrated nervous system would then face specific difficulties in 1G. The stronger gravitational signals would feel wrong. The postural reflexes calibrated for 0.38 G would be inappropriate for 1G. The sense of balance appropriate for Mars would be inadequate for Earth. These are all predictions from first principles, from the general principle that biological systems calibrate to their environments during development. They are plausible and consistent with what we know about developmental plasticity in biological systems, but they are not data. The specific magnitude of each of these effects in 0.38 G specifically, as opposed to zero gravity, which we have studied, is unknown. The interactions between these effects are unknown. The compensatory mechanisms that might mitigate some of them are unknown. What we can say with confidence is that a person who develops from conception through adulthood in 0.38 grams will be physiologically different from a person who develops in 1 gram. Not different in their genetics, but different in the expression of that genetics in response to the gravitational environment. The differences will make them well adapted to Mars and less well adapted to Earth. Whether less well adapted means inconveniently less adapted or dangerously less adapted is the question that cannot be answered without data we do not have. Let us now talk about the reproduction question, because reproduction is where the colonization question becomes most acute and most uncomfortable. Human reproduction is extraordinarily sensitive to physiological conditions. The process of conception, implantation, and early embryonic development involves complex hormonal signaling, precise timing of developmental events and physical processes, the movement of eggs and sperm, the implantation of the blastocyst in the uterine wall, that occur in a gravitational environment. Whether any of these processes are affected by gravity is largely unknown. Some relevant animal data exists. Studies of reproduction in space have been conducted with simpler organisms, frogs, newts, mice, and the results are mixed and difficult to generalize. Frog eggs, fertilized in microgravity, showed abnormal development in some studies. Mice, conceived and born in simulated microgravity, showed altered development in some studies. The extrapolation from these animal studies to human reproduction is uncertain. The specific mechanisms of mammalian reproduction vary substantially between species. For human reproduction specifically, we have essentially no data from reduced gravity environments. The ethical constraints on reproductive experiments in space are substantial and appropriate. No human pregnancies have been attempted in space. No data exists on whether human embryonic development proceeds normally in 0.38 g. No data exists on whether the complex hormonal environment of human pregnancy is disrupted by reduced gravity. No data exists on whether fetal development in 0.38 g produces normal fetal physiology. This is the most profound gap in our knowledge about Mars colonization. The entire enterprise of establishing a self-sustaining human presence on Mars requires that humans on Mars can reproduce and that their children can be born healthy and develop normally. If human reproduction in 0.38 g is substantially impaired, if conception is difficult, if implantation fails at elevated rates, if fetal development is disrupted by the gravitational environment, if birth outcomes are worse in 0.38 g, then the foundation of the colonization enterprise is undermined. We do not know whether any of these things are true. They may not be. Human reproduction may be robust to 0.38 g in ways that are impossible to predict from first principles. Or it may not be. And the only way to find out is data. Data that we do not have and that would be extraordinarily difficult and ethically fraught to obtain. The ethical dimension of reproduction in reduced gravity deserves explicit attention. If a couple on Mars chooses to conceive, they are making a decision not just for themselves, but for their child, a child who will develop in a gravitational environment of unknown physiological consequences. The parents cannot know whether their child will be healthy in 0.38 g. They cannot know whether that child will ever be able to visit or live on Earth. They cannot know what the long-term physiological consequences of developing in 0.38 g will be for a human being who will live with those consequences for their entire life. The child cannot consent to being born under these conditions. This is an ethical question with no clean answer. Human exploration and colonization have always involved bringing children into difficult and dangerous conditions. The children of the first settlers of the Americas, the children of 19th century frontier families, the children of 20th century Antarctic researchers. These analogies are real. But Mars is different in the specific sense that the unknown here is not whether the conditions are harsh. Everyone knows they are harsh. But whether the conditions will affect the fundamental developmental biology of the children born there in ways that are permanent and irreversible and that have never before been imposed on any human being. The question of informed consent for children cannot be resolved because children cannot consent. The parents' consent to the risk is real. They are informed adults making voluntary choices. The child's consent is impossible. This is true of all parental decisions that impose conditions on children, including the decision to have children at all in difficult circumstances. But the Mars case is unusual in the specific nature of the unknowns involved. Not just harsh conditions, but unknown physiological consequences of an entirely novel gravitational environment. Mission planners and the organizations pursuing Mars colonization have not addressed this question in any serious public way. SpaceX's public communications about Mars colonization describe a city of 1 million people, but do not discuss whether human reproduction in 0.38 g is viable. NASA's planning documents address the radiation risks and the physiological challenges of transit and surface operations, but do not substantively address the reproductive biology question. The popular science coverage of Mars colonization discusses the engineering challenges in detail, but routinely skips past the reproductive biology question as though it does not exist. It exists. It is one of the most important unanswered questions about the viability of permanent human presence on Mars, and it has received a fraction of the scientific and public attention that it deserves. Let us now talk about what would actually be needed to answer the gravity question. What research program would be required to provide the data needed to make honest statements about the physiological viability of Mars colonization? The most direct approach would be long-duration human studies at 0.38 g in orbital habitats equipped with centrifuges capable of simulating Mars gravity. The technology for doing this exists in principle. Rotating sections of orbital habitats or dedicated centrifuge modules can produce artificial gravity at any desired fraction of 1 g. What does not exist is a habitat large enough and operational long enough to conduct meaningful, long-duration physiological studies at 0.38 g. The ISS does not have this capability. The Gateway, the small lunar orbital station being developed as part of the Artemis program, will not have this capability as currently planned. Building the infrastructure needed to conduct meaningful 0.38 g physiology studies would require a dedicated orbital facility with rotating sections capable of sustaining the required centripetal acceleration, equipped with the medical monitoring equipment needed to track physiological parameters in detail, and staffed by research subjects willing to spend months at 0.38 g in what would essentially be a medical research environment. The cost of such a facility would be substantial, probably in the range of several $billion, and the research program would take years to produce results. Shorter-term partial gravity studies on the Moon are another option. The Moon has approximately 1/6 Earth's gravity, 0.17 g, which is below Mars gravity and not directly applicable, but lunar surface operations could provide data on human physiology in partial gravity that at least partially informs the Mars question. NASA's Artemis program is planning extended lunar surface operations. If those missions include systematic collection of physiological data, bone density, cardiovascular function, visual acuity, hormonal profiles, they will provide some relevant data, even though lunar gravity is not the same as Martian gravity. Animal studies at 0.38 g in orbital centrifuges could provide developmental data that would be ethically impossible to collect from humans. Studies of rodent reproduction and development at 0.38 grams, monitoring pregnancy outcomes, neonatal physiology, growth and development of young animals, would provide important information about whether mammalian development is disrupted at Martian gravity, even though rodent physiology differs from human physiology in many relevant ways. None of this research is currently funded and underway at the scale needed to answer the question before the first human Mars missions that some organizations are targeting for the 2030s. The timeline mismatch is stark. The earliest realistic human Mars missions could occur within 15 years. The physiological research program needed to characterize the effects of long-term 0.38 grams exposure would take at least that long to design, implement, and analyze if started immediately. It has not been started. This means that the first humans to go to Mars will be going without the physiological data needed to make informed decisions about long-term habitation in 0.38 g. They will be test subjects in an experiment that has not been approved by any ethical review board and that they cannot fully consent to because the risks are not quantified. This is not necessarily wrong. Exploration has always involved going before all the data is in, but it should be acknowledged honestly rather than obscured behind enthusiasm about the engineering challenges that are being solved. Let us talk about what the possible outcomes are and what each of them would mean for the vision of Mars colonization. The optimistic outcome is that 0.38 g is above the threshold needed for human health, that the gravitational loading of 0.38 g is sufficient to prevent or substantially reduce the pathological bone loss, cardiovascular deconditioning, and SANS that occur in zero gravity. That human reproduction is viable in 0.38 g. That human development proceeds normally enough at 0.38 g to produce healthy adults who are not severely impaired in Earth gravity, even if they are somewhat less adapted to it than Earth-born people. In this outcome, the gravity problem is manageable and colonization is physiologically feasible. This is the outcome that the proponents of Mars colonization are implicitly assuming. It may be correct. If it is correct, then the conversation about Mars colonization can proceed as it is currently proceeding, focused on the engineering challenges, the economic challenges, the psychological challenges, and the gravity question is a manageable complication rather than an existential obstacle. The pessimistic outcome is that 0.38 grams is insufficient for long-term human health, that bones continue to thin over years in 0.38 grams, even with exercise, until they reach a threshold of fragility that significantly increases fracture risk, that cardiovascular function continues to deteriorate over decades, that SANS develops progressively over years of exposure, that reproduction is impaired at significant rates, that child development in 0.38 grams produces physiological profiles incompatible with healthy adult function in 1 gram and potentially incompatible with healthy adult function even in 0.38 grams if the developmental process itself is disrupted. In this outcome, Mars colonization is not impossible, but it requires solutions that do not currently exist. Artificial gravity in habitats, rotating sections of the colony that produce 1G or near 1G, would be the primary response. People would live, exercise, and sleep in the rotating sections. They would venture into the Martian surface environment in spacesuits, aware that they were accumulating physiological costs that needed to be offset by time in artificial gravity. Pregnant women would spend their entire pregnancy in artificial gravity. Children would be raised in artificial gravity. The Martian surface would be a working environment rather than a living environment. This is a viable vision, technically challenging, but not physically impossible. Rotating habitat sections can be built. The engineering is understood in principle, even if not implemented in practice at the required scale. But it is a fundamentally different vision from the one usually presented. The image of Mars colonization as humans living on the surface of a new world, exploring its deserts, building their cities under dome structures, farming the soil, would need to be replaced by an image of humans spending most of their lives in rotating cylinders with occasional excursions to the surface. Not Mars as a new Earth, Mars as an orbital station that happens to be attached to a planetary surface. The intermediate outcome, and perhaps the most likely, is that 0.38 g is sufficient for some purposes but not others, and that the specific requirements of different activities and different life stages create a complex picture that does not yield to simple characterization. Adults may tolerate 0.38 grams for extended periods with acceptable health consequences if they exercise rigorously and take appropriate medical countermeasures. Reproduction may be viable with specific medical support. Child development may be acceptable in 0.38 grams if children also spend significant time in artificial gravity during critical developmental windows. The colony would need to manage the gravity environment actively. Different people in different phases of life spending different amounts of time in different gravitational environments, rather than simply accepting whatever gravity the planetary surface provides. Managing this complexity requires infrastructure and medical sophistication that goes well beyond what the earliest Mars missions would have available. Early settlements would be focused on survival, on establishing resource production, on building the basic infrastructure of habitation. The medical complexity of managing partial gravity through a combination of planetary surface exposure and artificial gravity would be a significant additional burden on a community that is already stretched to its limits. Let us talk about the specific medical technologies and approaches that could, in principle, mitigate the gravity problem, because saying that gravity is a challenge is only useful if we also examine what responses to that challenge actually look like in practice. The most obvious response is exercise. The ISS experience has established that rigorous exercise substantially reduces but does not eliminate the physiological deterioration of zero gravity. The exercise protocol on the ISS requires approximately 2 hours per day of combined aerobic and resistance exercise, a significant time commitment that also requires specialized equipment that takes up substantial volume and mass. In Martian gravity, the required exercise would presumably be less intensive than in zero gravity because some gravitational loading is already present, but the specific exercise protocol that would minimize physiological deterioration in 0.38 g has never been determined because no one has ever conducted that study. Exercise is a mitigation for adults with fully formed physiologies. It is a less adequate response to the developmental question. You cannot prescribe an exercise regime to a developing fetus. You can prescribe exercise to a growing child, but the effectiveness of exercise in replacing gravitational loading during the critical developmental windows of bone, muscle, and cardiovascular formation in 0.38 g is unknown. Children in Earth gravity build their musculoskeletal systems through the ordinary activities of childhood: running, jumping, climbing, falling, in a gravitational environment that automatically loads every movement. In 0.38 g, those same activities load every movement with less than half the gravitational force. And it is not clear whether the spontaneous exercise of childhood in 0.38 g is sufficient to drive normal development, or whether specific additional loading would be required. Pharmacological approaches exist for some aspects of the gravity problem. Bisphosphonates, medications that inhibit bone resorption, have been used in some astronauts to reduce bone loss during long-duration missions. They have been shown to help preserve bone density in microgravity in conjunction with exercise. Their long-term use raises concerns because they work by inhibiting osteoclasts, and prolonged inhibition of bone resorption can impair the bone's ability to repair microdamage and can eventually lead to atypical fractures. They are not a permanent solution for lifetime use in 0.38 grams. They are a tool for specific, limited applications. Cardiovascular countermeasures include lower body negative pressure devices, suits that apply suction to the lower body, pulling fluid downward and challenging the cardiovascular system to respond, and medications that affect blood pressure regulation. These have been used on the ISS with some success, but again, they are not permanent solutions for lifetime use, and their effectiveness at 0.38 grams rather than zero gravity is not well characterized. For the visual changes associated with SANS, the primary proposed countermeasure is the same as for the other problems, avoiding prolonged microgravity rather than treating the condition once it has developed. There is no established pharmacological treatment for SANS. The structural changes to the optic nerve and eye that occur in long-duration microgravity are in some cases permanent. Whether similar changes occur in 0.38 gram and whether they would be progressive over years and decades is unknown. None of these pharmacological approaches addresses the developmental question for children. Prescribing bisphosphonates to children to prevent bone loss in 0.38 grams would be medically unprecedented and ethically complex. The long-term effects of these medications on developing bone physiology are unknown. No pharmacological protocol exists for ensuring normal cardiovascular development in 0.38 grams. The pharmacological toolkit for managing 0.38 grams over a lifetime from conception to old age does not exist and would need to be developed entirely from scratch. Nutritional approaches, ensuring adequate calcium and vitamin D intake, optimizing protein and micronutrient availability for bone and muscle health, are important supporting measures, but are not primary solutions. Nutrition affects how well a given gravitational loading drives bone formation, but it does not substitute for gravitational loading. A person with excellent nutrition in 0.38 grams will do better than a person with poor nutrition in 0.38 grams, but may still not do as well as a person with adequate nutrition in 1 gram. The rotating habitat approach is the only proposed solution that actually addresses the root cause rather than mitigating its effects. If humans live in sections of their habitat that rotate to produce 1G or near 1G, then the gravitational loading issue is resolved directly. The developing skeleton forms in 1G, the cardiovascular system develops in 1G, the SANS does not develop because intracranial pressure is normal in 1G, and all the other gravity-dependent physiological processes occur in their appropriate gravitational context. The practical implementation of rotating habitats on Mars is challenging but not impossible. A centrifuge module within a larger habitat structure, a section that rotates around the long axis of a cylindrical habitat, could produce centripetal acceleration equivalent to 1G at a radius of several meters if rotating at an appropriate speed. The engineering is understood. The materials are available in principle. The integration with a larger habitat structure on the Martian surface would require careful design to ensure that the rotating section can interface with the non-rotating sections in a way that allows movement between them. The psychological experience of living in a rotating environment deserves consideration. Rotation rates high enough to produce 1G at small radii produce Coriolis effects, fictitious forces that deflect moving objects, that humans find disorienting and that can cause nausea and balance problems. The threshold rotation rate above which Coriolis effects become intolerable varies between individuals, but is generally considered to be around 2 rotations per minute for most people after an adaptation period. To produce 1G at 2 rotations per minute requires a rotation radius of about 224 meters, the radius of a very large structure. Smaller structures rotating faster would be more practically feasible, but would require inhabitants to adapt to significant Coriolis effects. This is solvable in principle. Humans can adapt to Coriolis effects to some degree. The threshold for tolerance increases with adaptation time, and the rotation requirement is not necessarily 1G. If the research establishes that 0.5 g is sufficient for healthy development, then the rotation radius required at any given rotation rate is halved. But again, the specific partial gravity threshold for human health is unknown, because the research has not been done. The cost and complexity of building and operating rotating habitat sections on Mars is significant and would add substantially to the already enormous challenge of establishing a viable Mars settlement. Every kilogram of rotating structure that must be brought from Earth or manufactured on Mars represents resources that are not available for other critical systems. The life support systems, the power generation, the food production, the water extraction, all of these compete for the same limited resources. Adding the complexity and cost of rotating sections to the habitation architecture is not trivial. For the very first missions, exploratory missions with small crews for limited durations, rotating habitat sections may not be practical or necessary if the crew members are adults accepting the physiological risks of 0.38 g for their short stays. For a genuine colonization effort, where families are living indefinitely and children are being born and raised, rotating sections may be not optional, but essential. The distinction between temporary missions and permanent colonization is where the gravity problem becomes most acute. Let us now address the question of what happens to the long-term evolutionary trajectory of a human population that lives on Mars for generations. Because if colonization is permanent, then eventually genetic and phenotypic change over generations becomes relevant. This is a subject that requires careful framing because it can easily be sensationalized in ways that are neither scientifically accurate nor productive. The timescale of genetic evolution, the change in allele frequencies in a population through natural selection, mutation, and drift, is thousands to tens of thousands of generations for significant changes. At roughly 25 years per generation, that is hundreds of thousands of years of human habitation before genetic evolution becomes a significant factor. No serious planning for Mars colonization needs to incorporate genetic evolution as a primary concern. What is relevant on shorter timescales is phenotypic plasticity, the capacity of a given genome to produce different physical characteristics in different environments during development. Humans show substantial phenotypic plasticity. The same genome produces different bone density, different muscle mass, different cardiovascular capacity, different immune function, depending on the environment in which the organism develops. This plasticity is not genetic change. The genome is the same, but the expressed phenotype can be substantially different. The Mars-born generation would express a different phenotype from their Earth-born parents, even if their genome is identical. The differences would be driven by the developmental plasticity of human physiology. The bones forming in response to 0.38 g, the muscles developing in response to 0.38 g demands, the cardiovascular system calibrating to 0.38 g, the vestibular system calibrating to 0.38 g. This phenotypic difference between Earth-born and Mars-born humans would be apparent within the first generation, and would compound over subsequent generations as each generation is born into an environment where the physiological baseline is set by Mars rather than Earth. Epigenetic changes, heritable changes in gene expression patterns that are not changes to the DNA sequence itself, could also contribute over several generations. If the Martian environment consistently produces specific patterns of gene expression through epigenetic mechanisms, those patterns might be transmitted to subsequent generations through epigenetic inheritance, a less well-established mechanism than genetic inheritance, but one that is increasingly recognized as real. The degree to which epigenetic changes in the Martian environment would be transmitted and accumulate over generations is genuinely unknown. Over generations, not thousands but dozens or hundreds, the Martian population would drift phenotypically from the Earth population in ways driven by both developmental plasticity and potentially epigenetic accumulation. Cultural and dietary differences would contribute additional divergence. The two populations would become increasingly distinct in their expressed characteristics, even before any genetic differentiation occurs. Whether this phenotypic divergence would eventually manifest as reproductive incompatibility, whether Earth-born and Mars-born people would remain capable of reproducing with each other, depends on whether the divergence affects any of the biological systems involved in reproduction. At the level of dozens of generations, this is almost certainly not an issue. At the level of hundreds of generations, it becomes a more open question. At the level of thousands of generations, which is the timescale at which genetic drift and selection might begin to produce meaningful genetic differentiation in an isolated population, speciation becomes a theoretical possibility. But this is so far in the future as to be irrelevant to any planning consideration. What is relevant on the timescale of initial colonization, the first few decades and centuries, is not speciation, but the practical question of whether Mars-born people can function on Earth, and whether Earth-born people can function on Mars after extended residence. The gravity problem makes both of these questions uncertain. Mars-born people may be effectively unable to live on Earth without significant medical support. Earth-born people who have spent decades on Mars may be similarly unable to return to Earth. These practical barriers to movement between the two worlds would be relevant within a few generations and would have implications for the social, economic, and political relationship between Earth and any Mars settlement. Let us talk about what the philosophical and ethical implications of the gravity problem are for the project of Mars colonization, not to argue for or against it, but to argue for intellectual honesty about what it actually entails. The standard public narrative about Mars colonization presents it as a straightforward extension of the history of human exploration and settlement. Humans have always gone to new places. They have always faced hardship. They have always adapted and eventually thrived. Mars is another new place. The hardships are different in kind and magnitude, but not in category. The human spirit of exploration and adaptation will prevail as it always has. This narrative is inspiring. It is also incomplete in a specific way that the gravity problem illuminates clearly. When humans colonized new continents or new islands on Earth, they found environments that were harsh in many ways, but that shared the fundamental physical constants of their origin: the same gravity, the same oxygen-containing atmosphere, the same solar irradiance level, the same basic chemistry. The adaptations required were cultural and physiological adjustments within the range of what Earth biology can handle. The people who came out of those settlements, however different their culture and their specific physical adaptations, were biologically the same kind of thing as the people who went in. Mars is different. The gravity is different. The atmospheric composition is different. The radiation environment is different. The solar irradiance is different. The soil chemistry is different. These differences are not merely challenging, they are fundamental. They require not just cultural and physiological adjustment within the range of Earth biology, but potentially adjustment beyond that range. They may require that humans who colonize Mars become, over generations, something that is meaningfully different from what they were when they left Earth. This is not necessarily bad. It is not necessarily good. It is genuinely novel. The question of whether the long-term trajectory of Mars colonization leads to a new branch of humanity, a population adapted to Mars in ways that make them different from Earth humans in physiologically significant ways, is not a science fiction speculation. It is a foreseeable consequence of the biology of development in a novel gravitational environment. How different and in what ways and on what timescale are the specific unknowns, but the direction toward divergence rather than sameness is predictable from first principles. The ethical implications of this divergence are serious. If establishing a permanent Mars colony means that the colonists and their descendants will become physiologically different from Earth humans in ways that reduce or eliminate their ability to return to Earth, then the colony is not simply a new human settlement in a new place. It is the establishment of a new kind of human existence that is essentially irreversible at the individual level, and that would, over generations, produce a population with a fundamentally different relationship to their planet of origin than any previous human colony has had. The people who go to Mars as adults are making a choice they understand, at least approximately. They know they are accepting physiological risks. They know they may not be able to return to Earth in good health after extended residence. They are consenting adults, making informed decisions under conditions of genuine uncertainty. The children born on Mars have not made any such choice. They will be born into a gravitational environment of unknown physiological consequences, in a world where their ability to visit or live on Earth is uncertain at best, where their long-term health trajectory is not yet understood, where the medical knowledge needed to care for them does not yet exist. They will be the subjects of the largest uncontrolled medical experiment in the history of the species. This is not an argument against colonization. Children born in difficult circumstances throughout history did not choose those circumstances, and many of them went on to contribute to the building of new societies. But it is an argument for intellectual honesty about what is being proposed and what it will cost, and what is unknown about the costs. The organizations pursuing Mars colonization, SpaceX above all, but also NASA and others, have not addressed these questions in any serious public way. The reproductive biology question, the child development question, the multi-generational divergence question, these are almost entirely absent from the public discourse about Mars colonization. This absence is not accidental. These are uncomfortable questions. They resist easy answers. They complicate the inspiring narrative. They suggest that colonization is more complex and more costly in specific ways that are hard to quantify and harder to market than the engineering challenges that can be illustrated with impressive renders of habitats and rockets. The engineering challenges are real and they are being worked on. The gravity problem is equally real, and it is not being worked on at the scale its significance demands. The research needed to characterize the physiological effects of long-term 0.38 G exposure, the centrifuge studies, the animal developmental studies, the long-duration partial gravity missions, is not funded or planned at the level that would provide the data needed before the first colonists arrive. This is not an argument for indefinite delay. There may be good reasons to accept the uncertainty and proceed anyway, reasons related to the long-term survival of the species, to the scientific value of direct Mars exploration, to the irreplaceable knowledge that can only be gained by going. These reasons are real, but they should be articulated clearly and the uncertainty should be acknowledged honestly rather than obscured behind engineering optimism. The conversation about Mars colonization would be better, more honest, more productive, more likely to lead to decisions that serve both the colonists and humanity, if the gravity problem were placed at the centre rather than the periphery. If the question of what 0.38 g does to human bodies over decades were asked loudly and funded generously and researched rigorously before the first colonists arrive rather than after. If the question of whether human children can develop healthily on Mars were treated as the foundational question it is, rather than as a detail to be worked out later. It may be that these questions have good answers, that 0.38 g turns out to be sufficient, that human development in 0.38 g proceeds normally enough, that the colonists and their children thrive. This would be wonderful, and it is certainly possible, but it should be established through research rather than assumed through optimism. And if the answers are not good, if 0.38 g turns out to be insufficient, if human development in 0.38 g is significantly impaired, if the physiological costs of permanent Mars residence are higher than the engineers and entrepreneurs have been assuming, then knowing this before sending the first colonists rather than after is better for everyone. Better for the colonists, who need accurate risk information to make genuine, informed consent decisions. Better for their children, who cannot consent, but deserve the best available medical knowledge to be applied to their care. Better for the project of Mars colonization itself, which will only succeed long-term if it is built on honest assessment of real challenges, rather than optimistic assumptions that do not survive contact with the actual physiology. Let us talk about what the ideal research program would look like. What steps, if started now, would provide the data needed to make honest statements about the viability of permanent human habitation in 0.38 g before the first colonists arrive? The first and most immediately actionable step is systematic collection of detailed physiological data from astronauts on the ISS. The ISS already provides long-duration zero-gravity exposure and the resulting physiological changes. What is needed is more systematic and comprehensive collection of data on individual variation in the physiological response to zero gravity. Why some astronauts develop severe SANS, while others show minimal changes. Why bone loss rates vary substantially between individuals. Why cardiovascular deconditioning follows different courses in different people. This individual variation data is crucial for understanding who might be most vulnerable to the effects of reduced gravity and for developing personalized countermeasure protocols. The second step is to establish, within the next decade, a research program using centrifuge facilities in orbit or on the lunar surface to study human physiology at fractional gravity levels, including 0.38 g. This requires building infrastructure that does not currently exist. The cost is significant but modest compared to the cost of a crewed Mars mission. The scientific value, the data on whether 0.38 g is above or below the threshold for long-term human physiological health, is foundational to the entire Mars colonization enterprise. The third step is a comprehensive animal research program in 0.38 g centrifuges studying reproduction and development. Rodent studies in simulated Martian gravity, measuring pregnancy outcomes, neonatal health, developmental trajectories of animals raised from birth in 0.38 g would provide critical data about whether mammalian development is disrupted at Martian gravity. The ethical considerations for animal research are less restrictive than for human research, and the results, while not directly applicable to humans, would substantially inform the human question. The fourth step is the development of medical protocols and countermeasure technologies specifically designed for 0.38 G, rather than adapted from zero gravity protocols. This includes optimal exercise regimens for 0.38 G, nutritional protocols, pharmacological countermeasures, and clinical monitoring guidelines. None of this can be done without the exposure data from steps 2 and 3, but the analytical and planning work can begin now. The fifth step, and the most ambitious, is to make the question of partial gravity physiology a central part of the planning for Artemis lunar missions. Extended human presence on the lunar surface at 0.17 G, below Martian gravity, but partial gravity nonetheless, would provide the first real data on how human physiology responds to sustained partial gravitational loading. While 0.17 G is not 0.38 G, the Moon provides the nearest available natural environment for studying partial gravity physiology, and the data would substantially inform the Mars question. None of this research program requires waiting for Mars colonization to begin. It can be started now with existing commitments to space exploration. The critical gap is not capability, but priority. The gravity physiology question is not receiving the research investment commensurate with its importance. Changing this would be one of the most valuable investments in the long-term viability of Mars colonization that could be made in the next decade. Let us now talk about what it means to take the gravity problem seriously in the context of the specific vision of Mars colonization that is most prominently promoted in public discourse. Elon Musk's vision of a self-sustaining Mars city of 1 million people is the most prominent and most detailed public articulation of the Mars colonization goal. It involves a timeline of establishing an initial settlement in the 2030s and growing it over decades to a city capable of sustaining itself without resupply from Earth. The vision is explicitly multi-generational. It requires not just the first settlers, but their children and grandchildren to build the city. It is a vision in which Mars-born people are essential participants, not just a hoped-for bonus, but a necessary component of the city-building enterprise. This vision is directly confronted by the gravity problem. A city of 1 million people on Mars requires 1 million people who are physiologically capable of doing the work of building and maintaining a city. If Martian gravity is insufficient for normal physiological function, those 1 million people need either rotating habitats that provide 1 G for essential biological functions, or they need to be descended from Earth-born people who have adapted to 0.38 G in ways that allow them to function adequately. And we do not know whether either of these options is achievable without the research that has not been done. The timeline of the vision, decades rather than centuries, makes the gravity problem particularly acute, because decades is not enough time for any of the gradual evolutionary processes that might provide some adaptation. The people building the city in 2050 and 2060 and 2070 will be people whose physiological challenges in 0.38 G are determined by the biology of individual development rather than by evolution. And the data on what those challenges are is not yet available. Taking the gravity problem seriously within the Musk vision would mean incorporating rotating habitat sections into the city design from the beginning, not as a later addition, but as a foundational element of the habitat architecture. It would mean funding the physiological research needed to characterize 0.38 grams effects now, so that the countermeasure protocols are ready when the colonists arrive. It would mean having a clear medical policy for reproduction in 0.38 grams, whether to recommend against natural reproduction until rotating sections are available, whether to require all pregnancies to be gestated in rotating sections, whether to defer reproduction until the physiological effects of 0.38 grams on adults are sufficiently characterized to make informed decisions. None of this is in the public vision as articulated. The public vision shows people walking on the Martian surface, farming Martian soil, building Martian cities. It does not show the rotating sections where they sleep, where they exercise, where their children develop, where pregnant women gestate. It does not discuss whether the Martian farmers can be healthy over decades, or whether their children will be able to visit Earth. These questions are not being asked in the public discourse because they complicate the inspiring narrative. They need to be asked. Not to kill the inspiration, the goal of establishing human presence on another planet is genuinely extraordinary and genuinely worth pursuing, but to ensure that the pursuit is as well informed as the challenge demands. The terrifying problem with colonizing Mars is not that it is impossible. It is that the most fundamental question about whether it is physiologically possible for the long term is not yet answered, is not being answered fast enough, and is not even being seriously asked in the conversations that are shaping the plans. The conversation needs to change. The gravity question needs to be placed at the center where it belongs. The research needs to be funded and executed. The honest acknowledgement of what we do not know needs to precede the enthusiastic announcement of timelines and city sizes. And then, with that honesty established, with that research underway, with the real scale of the challenge genuinely understood, the conversation about Mars colonization can proceed on the foundation of truth rather than the foundation of optimism. It will be a harder conversation. It will produce more complicated answers. It will take longer and cost more than the enthusiastic visions suggest. It will also be a conversation that actually prepares us for what Mars colonization is, not an adventure of the kind that humans have always had, in new but fundamentally familiar environments, but something genuinely new. A step into a gravitational environment we have never experienced. A commitment to a world that will make us different. A choice, made partly on behalf of people who cannot yet make choices for themselves, to become something that has never existed before. That choice deserves honesty. The gravity problem is the place where the honesty is most needed and most absent. Filling that absence is where the conversation about Mars needs to go next. Let us talk about what the gravity problem means in the context of the broader competitive landscape of space exploration. Because Mars colonization is not being pursued in a vacuum of pure scientific aspiration. It is being pursued in a specific geopolitical and commercial context that affects what questions get asked, what research gets funded, and what risks get acknowledged versus minimized. SpaceX is a private company with specific commercial and philosophical goals. Elon Musk has stated explicitly that the primary motivation for Mars colonization is the survival of the human species, the establishment of a backup civilization on another planet as insurance against extinction-level events on Earth. This is a legitimate and serious motivation that has been articulated by many thinkers beyond Musk. But it creates a specific dynamic in how the Mars project is presented and pursued. A company pursuing a product, in this case the product being a Mars settlement, has incentives to emphasize what works and what is achievable, and to minimize what is uncertain and what might not work. This is not necessarily cynicism. It is the normal psychology of ambitious goal pursuit. You do not build rockets by dwelling on all the ways rockets can fail. You build them by focusing on solving the problems you can solve and accepting the risks you cannot eliminate. The same psychology that makes SpaceX extraordinarily good at building rockets and launching satellites creates a systematic bias toward optimism about the challenges that are not yet confronted directly. The gravity problem is a challenge that SpaceX cannot currently confront directly, because confronting it requires physiological research that is not in SpaceX's core competency, and that would require a decade or more of careful scientific work before producing actionable conclusions. The company's planning horizon and the pace of its development programs do not naturally accommodate that kind of long-term scientific investment in questions that might produce uncomfortable answers. NASA operates under different constraints, as a government agency with scientific as well as exploration missions, with congressional oversight, with requirements for risk assessment and astronaut safety. NASA has stronger institutional incentives to ask the uncomfortable questions. But NASA's current focus on the Artemis moon program and the political and budgetary pressures on the agency's Mars planning mean that long-term physiological research for Mars colonization, as opposed to short-duration exploration missions, is not currently a funded priority. China's space program is pursuing lunar and eventually Mars exploration with explicitly nationalistic goals, the establishment of Chinese presence in space as a demonstration of technological capability and national power. The specific questions about long-term physiological viability of Mars habitation are unlikely to be primary considerations in Chinese space policy, which prioritizes milestones and demonstrations over scientific caution. The result of this competitive landscape is that no major actor in the space exploration arena has a strong institutional incentive to invest heavily in the kind of long-duration, partial gravity physiological research that would characterize the gravity problem honestly before colonization begins. The research would produce data that might slow down timelines, complicate messages, and create uncomfortable requirements. Every actor in the system has stronger incentives to proceed on optimistic assumptions and deal with the physiological problems as they emerge, rather than before they emerge. This is not a conspiracy. It is not even deliberate negligence. It is the predictable outcome of institutional incentives operating on a genuinely difficult problem that does not fit neatly into any of the current planning frameworks. But it is a problem, a collective action problem in which the research that is most needed is least likely to be funded by any single actor. And it needs to be named clearly. The solution to collective action problems is usually institutional. A governing body, a treaty, a shared standard that creates obligations for all actors. In the context of Mars physiological research, this would look like an international scientific agreement to share physiological data from all long-duration space missions, to establish minimum standards for physiological research that accompanies any crewed Mars mission, and to fund the specific research programs, orbital centrifuge studies, lunar surface physiology programs, animal developmental studies in partial gravity, that none of the individual actors has strong incentives to fund alone. Such an agreement is not unprecedented. The Antarctic Treaty of 1959 established a framework for international cooperation in Antarctic research that has allowed the scientific potential of that extreme environment to be realized, while managing the political and national competition that might otherwise have fragmented access. Something analogous for Mars, not on the geopolitical level, but on the scientific research level, would be valuable. The Artemis Accords, the bilateral agreements that NASA has been signing with various countries to establish principles for space exploration could potentially serve as a vehicle for this kind of scientific coordination, though they have not yet done so for the specific question of Mars physiology research. Let us now talk about the history of the gravity problem in the scientific literature, because the question of what partial gravity does to human physiology is not new, and understanding why it has received so little attention, despite being recognized for decades, is part of understanding why it remains unaddressed. The question of whether partial gravity is sufficient for long-term human health was first systematically articulated in the context of space station design in the 1970s. NASA's planning for large space stations in that era involved proposals for rotating sections to provide artificial gravity. The space station Freedom designs of the 1980s included rotating segments in some concepts. The physics and engineering of artificial gravity in orbital habitats were studied in some depth. The specific physiological threshold, what fraction of 1 gram is sufficient for long-term human health, was identified as a key unknown that research was needed to address. That research was not conducted. The large rotating space station designs were never built. The ISS that was eventually built, smaller, less expensive, politically more achievable, does not rotate. The physiological research program that should have accompanied the planning for long-duration spaceflight was never funded at the level required. Decades later, the question remains as open as it was when it was first identified. The history of why the research was not done is a history of changing priorities, competing demands, and the systematic subordination of long-term physiological science to short-term mission objectives. Each generation of mission planning acknowledges the importance of the gravity physiology question and defers its resolution to the next phase of planning. The result is that we are now contemplating Mars colonization in the 2030s with essentially the same state of knowledge about 0.38 g physiology that we had in the 1970s, which is to say, almost none. This is not unique to the gravity physiology question. The history of space medicine is full of research programs that were identified as essential, funded partially and briefly, and then deprioritized as mission objectives changed or budgets tightened. The bone loss problem was recognized as serious in the early Skylab era in the 1970s and has still not been fully solved 50 years later. The SANS problem was not systematically identified until the 2000s, despite the ISS having operated since 2000 and despite earlier hints in shorter missions. Space medicine has consistently been the poor relation of the engineering and operational programs that define the primary mission objectives. For Mars colonization specifically, this pattern is dangerous, because the physiological challenges of a permanent Mars settlement are not challenges that can be solved incrementally as they emerge. If you discover after the first generation of Mars-born children that 0.38 g is insufficient for normal development, you cannot undo the developmental consequences for those children. If you discover that reproduction in 0.38 grams has significant complications after the first pregnancies, you cannot retroactively provide the rotating habitat sections that were not built. The consequences of getting this wrong are irreversible in a way that most engineering failures are not. This irreversibility argument is the strongest case for prioritizing the gravity physiology research now rather than later. Engineering failures on Mars can be repaired or worked around with sufficient resources and ingenuity. Physiological failures that affect development are permanent in the individuals affected. The first Mars-born children will not get a second chance at childhood in the correct gravitational environment if the first one goes wrong. Getting the physiological question right before the first pregnancies occur on Mars is not a matter of caution for its own sake. It is a matter of the welfare of specific individuals who will exist and who will live with the consequences of decisions being made now. Let us talk about what the comparison to other extreme human environments tells us, because Mars is not the first environment in which humans have attempted to live under conditions that are physiologically challenging and poorly understood. Antarctic research stations provide one of the closest terrestrial analogies to Mars habitation. Small, isolated communities in extreme environments with limited resupply and the psychological challenges of months-long confinement. The comparison is frequently made in discussions of Mars habitability, and it is useful as far as it goes. Long-duration Antarctic expeditions have produced substantial data on the psychological effects of isolation, on the physiological effects of cold, on the social dynamics of small groups in confined spaces. This data is genuinely relevant to Mars mission planning. But Antarctic environments do not change human gravity. Antarctic researchers return from their expeditions with essentially the same physiology they arrived with: cold-adapted, vitamin D deficient, somewhat physically and psychologically stressed, but not fundamentally physiologically altered in the way that years in 0.38 G would alter a Mars resident. The Antarctic analogy is useful for psychology and social dynamics and some aspects of medical isolation. It does not address the gravity question at all. High-altitude environments provide a different analogy. Populations living at extreme altitudes, the Tibetan Plateau, the Andean highlands, have adapted over generations to low oxygen partial pressures that would be acutely dangerous for sea-level adapted humans. The Tibetan and Andean populations show genetic and physiological adaptations to hypoxia that are not present in their low-altitude relatives. These adaptations are real examples of human biology responding to an extreme environmental challenge over evolutionary timescales, thousands of generations, not dozens. The high-altitude case is instructive because it shows that humans can adapt to physiologically challenging environments, but also because it shows that the adaptation required thousands of years and was driven by strong natural selection. The individuals less adapted to altitude had worse survival and reproductive success, which, over generations, shifted the population toward the adapted phenotype. This is precisely the kind of adaptation that would not be available to Mars colonists on any near-term timescale, and that should not be relied upon as a solution to the gravity problem. The history of submarine crews provides another partial analogy. Confinement, isolation, limited space, separation from sunlight and normal environmental cues. Submarine crews experience these challenges for months at a time, and the psychological literature on submarine habitability has informed space mission planning. Again, the analogy does not address gravity. Submarines operate at normal atmospheric pressure and Earth's gravity. The physiological challenges of submarine service, while real, are not the challenges of Mars. Deep-sea diving operations, specifically saturation diving, in which commercial divers live for weeks at a time under pressure at depth, provide data on human physiology in hyperbaric environments. This is relevant to the pressure environment of habitats on Mars, where pressurization is necessary for survival, though Martian habitats would operate at pressures lower than Earth's surface rather than higher, as in saturation diving. The analogy is partial, and the direction of the pressure challenge is reversed. None of these terrestrial or Earth-adjacent analogies adequately captures the specific challenge of long-term 0.38 g exposure. The closest analogue for what Mars would do physiologically to human beings is the ISS data on zero gravity, which is more extreme than Mars gravity in the direction that matters. And that data, while valuable, tells us about zero gravity specifically, rather than about the intermediate case of 0.38 g that Mars represents. This is why the centrifuge studies are so important and why their absence from current research planning is so significant. Without 0.38 g specific data, all planning for Mars physiology is based on extrapolation from data that sits on either side of the relevant range. You know what happens at 0, you know what happens at 1. You are making plans for 0.38 based on the assumption that the physiological response changes smoothly and predictably between these two endpoints in a way that places 0.38 grams on the acceptable side of the threshold. That assumption may be correct. It may not be. And the stakes of getting it wrong are high enough that validating it before colonization begins rather than after should be a priority. Let us now talk about what we do know that is actually reassuring, because intellectual honesty about the gravity problem does not require pretending that all the evidence points toward catastrophe. Some of the evidence is genuinely encouraging, and it deserves acknowledgement. The most encouraging piece of data is that the ISS experience, while documenting significant physiological changes in zero gravity, has also demonstrated that these changes are substantially reversible, with rehabilitation after return to Earth. Astronauts who have spent 6 months in microgravity and returned to Earth have, with appropriate rehabilitation, largely recovered their pre-flight physiological baselines within months to a year. This reversibility suggests that the physiological changes of reduced gravity are adaptive responses rather than permanent damage. The body responds to reduced gravitational loading by recalibrating its physiology downward, and when loading is restored, it recalibrates back upward. This reversibility is encouraging for Mars in 2 ways. First, it suggests that the physiological changes that would occur in 0.38 g might also be largely reversible. That people who spend years on Mars could, with appropriate rehabilitation, recover physiological function if they return to Earth, or if they transition to artificial gravity sections of their habitat. Second, it suggests that the body has considerable adaptive capacity that might allow it to function adequately across a range of gravitational environments, rather than requiring a precisely fixed gravitational level. The Scott Kelly data, comparing a year-long ISS mission to the Earth-bound control of his twin, found that most of the physiological changes were reversible within approximately a year after return. The changes that persisted, some cognitive alterations, some persistent DNA methylation changes, some structural changes associated with SANS, are concerning but do not appear to be disabling. A year of serious physiological changes that mostly reverse with rehabilitation is troubling but not catastrophic for adult crew members on time-limited missions. The key uncertainties are whether this reversibility applies to 0.38 g specifically, whether it applies to exposures longer than the year that is the current record for continuous spaceflight, and crucially, whether it applies to developmental exposure, whether a physiology formed in 0.38 g can reverse its adaptations as effectively as an adult physiology that was formed in 1 g. The adult reversibility data from the ISS does not answer the developmental question, because the mechanisms of developmental plasticity are different from the mechanisms of adult adaptation and readaptation. The exercise countermeasure data is also somewhat reassuring. The intensive exercise programs on the ISS have substantially reduced bone loss compared to early missions that did not have equivalent exercise infrastructure. The current ISS exercise protocol, while imperfect, reduces monthly bone loss in weight-bearing bones from rates that would produce severe osteoporosis in short periods to rates that are more manageable over 6-month missions. If exercise at 0.38 g, where some gravitational loading is already present, can be shown to maintain bone density adequately, the bone loss problem may be manageable without requiring rotating habitats. The animal research data on reproduction, while incomplete and difficult to extrapolate to humans, is not uniformly alarming. Rodents born and raised on the ISS in microgravity have been studied, and while they show physiological differences from Earth-raised controls, they are not uniformly unhealthy. The developing mammalian organism appears to have some capacity to adapt to reduced gravitational loading that partially compensates for the absence of normal loading. Whether this compensatory capacity is sufficient for 0.38 g and for the more complex physiology of human development is unknown, but the existence of the compensation is at least somewhat encouraging. These reassuring data points do not resolve the gravity problem. They narrow the range of possible outcomes toward the less catastrophic end, but they do not establish that 0.38 g is safe for long-term human habitation and development. The honest position is that we have reasons for cautious optimism, but not for the confident optimism that characterizes the public discourse about Mars colonization. The difference matters for planning purposes. Cautious optimism argues for proceeding carefully with extensive physiological monitoring and contingency planning, while confident optimism argues for proceeding full speed ahead, and these lead to very different mission architectures. Let us talk about what the appropriate response to the gravity problem is, not in policy terms or research planning terms, but in terms of the conversation itself. How should we be talking about Mars colonization, given what we know and what we do not know? The appropriate response is not to stop talking about Mars colonization, or to argue that it should not be attempted. The scientific case for human Mars exploration is strong. The long-term strategic case for establishing a human presence beyond Earth is real. The technological development that Mars colonization would drive has value beyond Mars itself, and the specific scientific questions that Mars poses about the history of water and the possibility of life in its ancient past are among the most important questions in science, and ultimately require human presence on Mars for their full resolution. The appropriate response is to change the framing, to bring the gravity problem to the center of the conversation rather than leaving it at the periphery, to ask loudly and publicly the questions that the current conversation is avoiding, to insist that the research needed to answer those questions be funded and executed on a timeline that is actually ahead of, rather than lagging behind, the colonization timeline. Specifically, this means asking whether any organization planning Mars colonization has a physiological research roadmap, a plan for what studies will be conducted, on what timeline, with what resources, to characterize the effects of long-term 0.38 g exposure before the first permanent residents arrive. If no such roadmap exists, and currently it does not appear to, asking why not and demanding one. It means asking whether any organization planning Mars colonization has a reproductive biology policy, a position on whether reproduction in 0.38 g will be encouraged, discouraged, restricted to rotating habitat sections, or addressed in some other way, and insisting that this question be confronted rather than deferred. The first Mars colonists will face this question whether or not the organizations that sent them have answered it. And unprepared colonists making unprepared reproductive choices under unknown physiological conditions is worse for everyone than having addressed the question in advance. It means insisting that the technical literature on Mars colonization, the engineering studies, the mission architecture documents, the habitat design specifications, treat the gravity physiology question as a first-order design requirement rather than as a secondary concern. If rotating habitat sections are required for long-term physiological health, that requirement should be in the habitat specifications from the beginning, rather than retrofitted after the first health problems emerge. It means supporting and promoting the specific research programs, orbital centrifuge studies, lunar surface physiology programs, animal developmental studies that would provide the data needed to answer the gravity question. These programs are not glamorous. They do not produce the kind of spectacular imagery that drives public engagement with space exploration. They produce careful medical and physiological data that is essential for knowing what you are doing before you do it. They deserve more attention and more funding than they currently receive. And it means being honest about uncertainty. When a prominent advocate of Mars colonization says that Mars is difficult but achievable, and that the first settlers will face challenges but will ultimately succeed, the appropriate response is to ask what evidence that claim is based on, specifically with regard to the long-term physiological effects of 0.38 grams. If the answer is that we do not yet have that evidence, which is the honest answer, then the appropriate framing is that Mars colonization might be physiologically achievable, but that we do not yet know, rather than that it is achievable with appropriate engineering solutions. The gravity problem is not a reason to give up on Mars. It is a reason to take Mars more seriously than the current conversation does. More seriously about what is unknown. More seriously about what research is needed. More seriously about what it would actually mean to commit to permanent human habitation of another planet in a gravitational environment that has never been experienced by any human being for more than a brief transit. Mars is worth the difficulty. It is worth the investment. It may be worth the risks that the gravity problem represents. But it is worth it in the way that genuinely hard things are worth it, by being approached honestly, with clear eyes about what is known and what is not, with the research and the planning and the institutional commitment that the difficulty actually demands. The terrifying problem with colonizing Mars is not that it cannot be done. It is that the conversation about doing it has not been honest about what doing it requires. The gravity problem is where the honesty is most needed. It is time for the conversation to change. Let us talk about what happens to human identity when gravity changes, because the gravity problem is not only physiological. It is also psychological, cultural, and philosophical in ways that the medical literature does not fully capture, but that are essential for understanding what Mars colonization actually means for the people who live it. Human beings have a deep and largely unconscious relationship with gravity. It is the constant background condition of every moment of every human life. Every movement you make, walking, reaching, sitting, lying down, is shaped by gravity's constant pull. Every object you handle has weight that gravity gives it. Every physical sensation of effort and rest is calibrated against gravity's demand. Every architectural environment humans have ever built, every room, every staircase, every door height, every chair, is designed for gravity at 1 g. the entire built environment of human civilization is an expression of 1g gravity. In 0.38g, this entire relationship changes. Not catastrophically. Mars has gravity, which is qualitatively different from weightlessness. Objects still fall. Up and down still have meaning. Physical effort is still required for movement. But quantitatively, everything is different. Things weigh less than half as much. Your body weighs less than half as much. The effort required to climb stairs, to lift objects, to stand from a seated position, all of it requires less than half the muscular effort it requires on Earth. The psychological experience of this is not straightforwardly pleasant or unpleasant. Astronauts returning from zero gravity frequently describe the overwhelming heaviness of Earth, the sense that gravity is crushing them after months of weightlessness. Mars residents returning to Earth, if they ever do, would experience something similar, though less extreme. Their bodies adapted to 0.38g would find 1g burdensome in ways that someone who has always lived in 1g cannot easily imagine. Conversely, a person adapted to 1g visiting Mars for the first time would likely find the reduced gravity initially disorienting. Movements would feel too easy. Physical feedback would be wrong. The calibrated sense of effort built over a lifetime in 1g would produce inappropriate responses in a world where everything weighs less. These are not merely inconveniences. They represent a profound change in the relationship between the body and the physical world, a change that happens slowly during adaptation and that eventually becomes the new normal. The Mars-adapted person who no longer finds it odd that rocks can be thrown much farther, that falls are less dangerous, that carrying heavy loads feels qualitatively different. This person has a fundamentally different embodied experience of the physical world from any human being who has ever lived before them. The cultural implications of this embodied difference are hard to predict, but worth considering. Human cultures are deeply shaped by the physical conditions in which they develop. The specific challenges of agriculture, construction, warfare, medicine, sport, all the activities that give cultures their particular character, are shaped by the gravitational environment in which they occur. A culture developing in 0.38g would face different physical challenges in all of these domains. Agriculture on Mars must deal with lower gravitational settling of soil and water, different dynamics of plant growth in partial gravity, different aerodynamic properties of atmospheric movement in the thin Martian air. Construction must account for different structural loading requirements. Buildings need less structural mass to support their own weight in 0.38g, which changes the economics and aesthetics of architecture. Sport and physical competition would be dramatically different. The human body capable of feats in 0.38g that are impossible in 1g, and the physical intuitions developed in 0.38g producing different competitive dynamics. A culture that develops in these conditions over generations will be culturally distinct from Earth cultures, not just because it is geographically isolated, but because the physical world it inhabits is fundamentally different. The relationship between human effort and physical outcome, the basic structure of how much you have to push to move the world, will be different. And cultures are shaped by their physical worlds in ways that go deep into language, metaphor, value, aesthetics, and self-understanding. The language question is particularly interesting. Languages are shaped by the physical and cultural environments in which they develop. The specific vocabulary for talking about weight, effort, lifting, carrying, falling, vocabulary that is embedded throughout the grammar and metaphor of every human language, was developed in a 1G world. A language developing on Mars would eventually develop different intuitions around these concepts, different ways of talking about effort and resistance, and the relationship between force and motion. Whether Mars colonists would develop a new language or significantly modify an existing one over generations is uncertain, but the physical environment would create pressure toward linguistic change in ways that are predictable, even if the specific changes are not. This cultural and linguistic divergence from Earth is not a problem to be solved. It is a consequence of genuine settlement, of building a civilization in a place that is genuinely different. The history of human expansion on Earth produced cultural and linguistic diversity precisely because different environments shaped different responses. Mars would do the same. The question is whether the people making decisions about Mars colonization now understand and accept that they are setting in motion a process that will eventually produce not just a new outpost of Earth civilization, but something that is genuinely different, culturally, physiologically, psychologically, from anything that has existed before. Let us talk about what the psychological literature on isolation and confinement tells us about the specific mental health challenges of Mars colonization, because the gravity problem has a psychological dimension that parallels its physiological one. The psychology of long-duration isolation is well studied from Antarctic expeditions, submarine deployments, remote research stations, and space missions. Common findings include increased irritability, social friction, depression, and cognitive dulling that appear reliably in isolated small groups, regardless of the specific physical environment. The third quarter phenomenon, a notable deterioration in mood and motivation approximately 3/4 of the way through a known duration isolation period, appears consistently across different isolation environments. Sleep disruption is common. Motivation decreases over time. The ability to maintain productive interpersonal relationships in a small, fixed group becomes increasingly strained. These effects are present even in isolation environments where people know the isolation is temporary. They know the Antarctic expedition will end, the submarine will surface, the space mission will conclude with return to Earth. The psychological burden of Mars colonization is qualitatively different in the specific sense that the isolation may not end. The colonist who intends to remain permanently on Mars, who understands that this is their life now, not a temporary mission they will complete and return from, faces a psychological situation that the Antarctic and submarine data does not capture. Permanent separation from Earth, from everyone and everything the colonist knew before departure, is a psychological event with no adequate precedent in the space medicine literature. The closest analogies are historical: emigrants who crossed oceans knowing they would likely never see their homeland again, settlers who moved to frontier territories with the understanding that the journey was one way. These analogies are real, and they show that humans can psychologically adapt to permanent separation from their origins. But they also show that the adaptation has costs. The grief of permanent separation is real. The challenge of building meaning in a new place without the social and cultural context of the original is real. The psychological demands of participating in the founding of a new community with no established norms or traditions is real. The first Mars colonists will face all of these challenges simultaneously with the physiological challenges of 0.38 G, the environmental challenges of the Martian surface, the technical challenges of maintaining life support systems, and the social challenges of living in a small community with high stakes and limited privacy. The cumulative psychological burden of all of these simultaneous challenges has never been experienced by any human being and cannot be fully simulated or prepared for in advance. The selection of psychologically appropriate candidates for Mars colonization is therefore one of the most important and least well-developed aspects of the mission planning. Current astronaut selection processes are good at identifying people who perform well under the specific stressors of space missions as currently conducted. High-performance professionals with strong technical skills, good team compatibility, and sufficient psychological resilience for 6-month to year-long missions with the knowledge of return. These characteristics are necessary, but not sufficient for the selection of people who will be permanently committed to a community-building enterprise on another planet. What additional psychological characteristics are needed for permanent Mars colonists that current selection processes do not specifically target? Several candidates emerge from the psychology of successful permanent settlers in historically extreme environments. The first is what psychologists call a growth mindset applied to the mission, a genuine belief that the difficulties and unknowns of the situation are not obstacles to be overcome on the way to a known destination, but the substance of the experience itself. Permanent Mars colonists need to find meaning not in the eventual completion of the mission, but in the ongoing process of building something new in a challenging environment. People whose psychological well-being depends on clear goals with defined endpoints will struggle in an environment where the endpoint is not defined and may never be. The second is a capacity for finding sufficient social connection within a small permanent group. The social world of early Mars colonists will be extremely limited. Dozens of people initially, perhaps hundreds later, but for many years a tiny community relative to what any of them were accustomed to on Earth. People who require the diversity and stimulation of a large social environment for their well-being will find Mars psychologically crushing, regardless of how technically prepared they are. People who can form deep attachment and find sufficient social fulfillment within a small, stable community, people for whom the depth of few relationships compensates for the breadth of many, are better psychologically suited to what Mars will actually offer. The third is a specific relationship to uncertainty, not merely tolerance for it, but something closer to comfort with it, the capacity to plan and work and invest in the future without knowing what the future holds, and without the security that comes from operating within established institutions and norms. Frontier communities require members who can function without the scaffolding of existing social structures, who can negotiate and establish norms rather than operating within them, who can make decisions about communal life without reference to precedent or authority. This capacity is not the same as independence or stubbornness. It requires the ability to negotiate and compromise within the small community, as well as to function without external guidance. These psychological characteristics are not routinely measured in current astronaut selection, and they are not the primary qualities that have been valued in the astronaut corps historically. The astronaut selection process evolved to identify people for technically demanding short to medium duration missions within well-established operational frameworks. Expanding it to identify the right people for permanent colonial settlement is a different and more complex challenge. The therapy and mental health support infrastructure for a Mars colony is also largely unplanned. Current ISS astronauts have regular access to psychological support, scheduled calls with personal psychotherapists, behavioral health monitoring, mission control psychologists who track crew dynamics and intervene when problems are identified. This support is valuable and demonstrably effective at managing the psychological challenges of 6-month missions. For permanent Mars colonists, separated from Earth by a communication delay of up to 22 minutes each way, the existing model of Earth-based psychological support is inadequate. Real-time intervention is impossible, and the asynchronous communication that replaces it is less effective for acute psychological crises. Developing AI-assisted mental health tools specifically designed for long-duration space missions is a research area that has received some attention. AI therapists that can engage with crew members in real time, monitor behavioral and physiological indicators of psychological distress, and provide interventions that do not require Earth-based human psychologists. These tools are in early development, and their effectiveness for the specific challenges of permanent Mars colonization has not been established. The gap between what current psychological support infrastructure provides and what a permanent Mars colony would require is substantial. Let us talk about what the economic structure of a Mars colony would look like, because the economic viability of permanent Mars habitation is as uncertain as the physiological viability, and for some of the same fundamental reasons. The economic argument for Mars colonization most commonly made is the long-term value of establishing a backup civilization and the eventual development of a Martian economy that may become self-sustaining and eventually large. These are real arguments, but they operate on very long timescales, decades to centuries, and they do not provide a clear economic model for the early settlement period, when the colony is entirely dependent on Earth for critical supplies, and when it cannot yet produce economic value that justifies the enormous cost of maintaining the supply chain. The supply chain itself is governed by the same orbital mechanics that constrain the physiological situation. Mars and Earth align for economical transfers only once every 26 months. Each transfer window allows a limited amount of cargo to be sent, cargo that costs somewhere between several thousand and tens of thousands of dollars per kilogram to deliver to the Martian surface, depending on the specific launch vehicle and mission architecture. The cost of supplying a Mars colony with the basic necessities of life for the period before it can produce those necessities itself — food, water, medical supplies, equipment, spare parts — would be astronomical in the literal and figurative sense. Elon Musk's economic model for Mars colonization relies on Starship achieving transportation costs to Mars sufficiently low that the supply chain becomes economically manageable, costs potentially in the range of hundreds of thousands of dollars per ton, rather than millions. If this cost reduction is achieved and sustained, the economic viability of early settlement becomes more plausible. If it is not achieved, if Starship's costs are higher than projected, or if the cadence of Mars missions cannot be sustained at the level needed, the supply chain costs could be prohibitive. The in situ resource utilization question is economic as well as technical. The Mars colonists who can produce their own water, oxygen, food and building materials from local resources are economically sustainable in ways that Mars colonists entirely dependent on Earth supply are not. The technical challenges of in situ resource utilization are substantial, but most of them are understood in principle. Water ice can be extracted and processed, CO2 can be converted to oxygen, local materials can be used for construction. The economic question is how long it takes for a Mars colony to reach the level of in situ resource production that substantially reduces its dependence on Earth's supply. The critical path is food production. Water and oxygen production are energy intensive but technically tractable. Food production in the quantities needed for a growing colony requires agricultural infrastructure that takes years to build and optimize. During the period before food production is established at scale, the colony depends entirely on imported food, At the costs per kilogram of Martian delivery, this is extremely expensive. The agricultural transition period, the years between arrival and sustainable local food production, is the most economically precarious period of any Mars colony and must be planned for with hard-nosed realism about what can actually be grown, in what quantities, in what timescale, in Martian conditions that have never been tested for real agricultural production. The laboratory experiments that have been conducted on growing plants in simulated Martian soil have produced mixed results. Martian soil, or rather the Martian regolith, is mineral-rich but lacks organic matter and contains perchlorates that are toxic to plants at sufficient concentrations. Remediation of the perchlorate contamination through washing or biological degradation is possible in principle. Adding organic matter through composting and biological inputs can build soil fertility over time. But the transition from raw Martian regolith to productive agricultural soil is not a rapid process. The first Mars colonists will be eating from Earth-supplied food stocks for years before their agricultural systems are mature enough to provide a substantial fraction of their calories. The economic structure of a Mars colony in its early years is therefore essentially that of a research station with an enormous ongoing supply cost, comparable to the cost of Antarctic research stations, but at distances and with supply frequencies that make the Antarctic case look economical by comparison. The justification for this cost in the Antarctic case is scientific research value. The justification for the Mars case is a combination of scientific value and the long-term strategic value of establishing a human presence on another planet. Whether governments and private investors will sustain the financial commitment needed to carry a Mars colony through the years before it becomes economically self-sustaining is one of the most important uncertainties in the colonization enterprise. The governance structure of a Mars colony is another critical question that has received remarkably little serious attention, given how much attention is given to the engineering challenges. A small community of people in an extreme and isolated environment making life or death decisions together needs governance systems that are appropriate to its conditions. Systems that can resolve disputes, allocate resources, manage individual rights against collective needs, and adapt to unexpected situations. The governance systems that work for Earth societies, democratic governments, market economies, legal systems with courts and enforcement, do not translate directly to a small, isolated community of dozens or hundreds of people on another planet. The history of small, isolated communities establishing their own governance from scratch, shipwrecked sailors, isolated colonies in extreme environments, is mixed. Some have established functional cooperative systems that allowed the community to survive and eventually thrive. Others have descended into conflict and dysfunction. The difference often comes down to whether the community had a prior basis of trust and shared values, whether its governance systems had legitimate authority in the eyes of all members, and whether the individual members were psychologically suited to the demands of communal decision-making under pressure. A Mars colony will have a prior basis of shared values, shared commitment to the mission, but the specific governance mechanisms will need to be established from scratch in an environment where the usual enforcement mechanisms of law do not apply. Earth cannot adjudicate disputes on Mars in real time. There is no police force, there is no court. The social contract that makes governance legitimate on Earth, the ability to exit if you disagree with the community's decisions, backed by alternative communities available elsewhere, does not exist when the only alternative to staying is the impossibility of leaving. This is a genuinely novel governance situation, and it deserves as much serious attention from political theorists, legal scholars, and social scientists as it gets from engineers. The literature on this specific question is thin. The people planning Mars colonization have not meaningfully engaged with it in their public communications. The first Mars colonists will be navigating this governance challenge without the benefit of serious prior work on what governance systems are appropriate to their specific situation. Let us now bring the gravity problem, the physiological question, the psychological question, the economic question, and the governance question together into a unified picture of what Mars colonization actually requires. What emerges from this synthesis is a picture that is simultaneously more inspiring and more daunting than either the enthusiastic promoters or the skeptical critics typically present. More inspiring because the challenge is genuinely extraordinary, not just technically difficult, but philosophically novel, requiring the creation of new human institutions, new human physiology over generations, new human culture, new human identity. The people who do this will not just be pioneers in the sense of facing physical danger. They will be founders in the deepest sense, creating forms of human existence that have never existed before, and that will shape whatever humanity becomes on timescales that dwarf the timescales of any previous human enterprise. More daunting because the honest accounting of what is unknown and what is needed is much more extensive than the public conversation acknowledges. The gravity physiology question is unresolved. The reproductive biology question is unresolved. The child development question is unresolved. The psychological requirements for permanent colonists are not well characterized. The governance model is not developed. The economic pathway from complete Earth dependence to self-sufficiency is not clearly mapped. The rotating habitat requirements, if they are requirements, are not incorporated into the mission architecture. The appropriate response to this picture is not despair, and it is not uncritical optimism. It is the kind of sober, clear-eyed engagement that genuinely hard challenges deserve. The challenges are real. They are addressable, not easily, not quickly, not cheaply, but addressable through sustained commitment and honest scientific inquiry. The path to addressing them begins with acknowledging them clearly, rather than obscuring them behind engineering enthusiasm. The gravity problem specifically needs to be elevated from a background concern to a foregrounded priority. It needs to be funded. It needs to be researched. It needs to produce data before the first permanent residents arrive on Mars, rather than after. The research program needed to address it is not exotic or speculative. It is concrete and designable and executable, with the technology and resources available today. What is missing is not capability, but priority. Changing that priority, putting the fundamental physiological question at the center of Mars colonization planning where it belongs, is the most important single step that the people planning Mars colonization could take. And the conversation needs to change to reflect the true complexity of what is being proposed. Not because complexity is a reason for pessimism, but because honest complexity is more useful than false simplicity. The people who will actually go to Mars, who will commit their lives and the lives of their children to an experiment in human existence on another planet, deserve an honest accounting of what is known and unknown about what they are accepting. They deserve a conversation that takes their challenge seriously enough to ask the hard questions, fund the necessary research, and build the governance and medical systems that the difficulty actually requires. Mars is worth it. The question of whether we are approaching it in the way that the worth of it demands is the question that the gravity problem forces us to confront. The answer, currently, is no. We are not approaching it in the way its worth demands. The most fundamental physiological question is unresolved and underfunded. The most important unknowns are under-acknowledged. The most daunting challenges are under-planned for. Changing this is possible. Changing this is what taking Mars seriously actually looks like. There is a specific kind of courage that the gravity problem asks for, and it is not the courage that space exploration is usually celebrated for. The celebrated courage of space exploration is the courage of going, of boarding a rocket knowing the risks, of accepting that the mission might fail and going anyway, of standing on the edge of what is known and stepping off. This courage is real, and it deserves the celebration it receives. The people who have gone to space, who have sat on top of controlled explosions and been flung into orbit and lived in floating metal cans for months, have demonstrated something genuine about human character that matters and that we should honour. The courage that the gravity problem asks for is different. It is the courage of not knowing, of admitting that the most important question has not been answered, of saying loudly, in the face of enthusiastic timelines and inspiring renders and the genuine excitement of a generation that wants to believe Mars is next, we do not know if this is possible in the way we are imagining it. We need to find out before we commit people's lives, and more importantly, their children's lives, to conditions we do not understand. This is harder courage. It is less photogenic. It does not produce the kind of imagery that goes viral. It does not make for inspiring speeches about the human spirit and our destiny among the stars. It produces careful scientific papers and research funding requests and ethics committee reviews and the kind of deliberate institutional work that nobody makes movies about. But it is the courage that Mars actually requires. Because Mars does not care about our timelines or our excitement or our inspiring narratives. Mars is what it is. 0.38 g of gravitational acceleration on every bone and muscle and cardiovascular system and developing fetus that spends time there. The question of what that does to human beings over a lifetime is a question with an answer, a real physical answer that exists independent of what we would prefer it to be. Finding out what that answer is before we send families to live there permanently is not caution for its own sake. It is the minimum standard of intellectual honesty that the situation demands. The terrifying problem with colonizing Mars is not really the radiation or the perchlorates or the dust storms or the 500-day minimum stay or the return rocket logistics or the psychological isolation, though all of those are real and serious. The terrifying problem is that the most fundamental question, can a human being develop and live a full, healthy life in 0.38 g, has not been answered and is not being answered on any timeline that precedes the colonization plans of the organizations most actively pursuing it. A child born on Mars in the 2040s, if the most aggressive timelines hold, will be born into a gravitational environment that no human being has ever experienced for more than the few hours of a brief lunar or planetary surface operation. That child's skeleton will form in 0.38 g. Their cardiovascular system will develop in 0.38 g. Their vestibular system will calibrate to 0.38 g. Their entire embodied sense of what the physical world feels like will be built in 0.38 g. And we do not know, we genuinely, honestly, scientifically do not know what kind of person that will produce, whether they will be healthy, whether they will be able to function adequately, whether they will ever be able to visit the planet their parents came from. That child cannot consent to being born under those conditions. They cannot choose their planet any more than any child chooses theirs. The parents can consent to go to Mars, and their consent, informed by honest accounting of the risks, is legitimate and real. The child's consent is impossible. What the child deserves in place of consent is the best available science applied to understanding their situation before it is too late to matter for them specifically. That science does not yet exist. It needs to be created. The orbital centrifuge studies need to be designed and funded. The animal developmental studies need to be conducted. The partial gravity human physiology data needs to be collected. The medical protocols for 0.38 grams, for adult health maintenance, for pregnancy management, for child development monitoring, need to be developed. The rotating habitat designs need to be incorporated into colony architecture if the data indicates they are necessary. All of this needs to happen before the first permanent residents arrive, not after. The people planning Mars colonization are mostly brilliant and mostly well-intentioned, and they are working on genuinely hard problems with impressive technical sophistication. They deserve credit for that. But they are not asking the hardest question, funding the most important research, or building their architectures around the most fundamental unknown. That is not a small gap. It is the gap between a Mars colonization effort that knows what it is doing and one that is, at its physiological core, making assumptions that have not been validated. We have been here before in the history of human settlement. Not with gravity, that is genuinely novel, but with the general pattern of moving people into conditions that are poorly understood and trusting that adaptation will occur, that the challenges will prove manageable, that human resilience will carry the day. Sometimes it does. Sometimes it does not. The history of colonial medicine is in part a history of the costs of not asking the medical question seriously enough before sending people into conditions that turned out to be more harmful than anticipated. Mars deserves better than that history. The people who will go there deserve better. Their children, born into a world they did not choose, in a gravitational environment that has never been inhabited before, deserve the best available medical knowledge applied to their care before they arrive, not as an afterthought when problems emerge. The gravity problem is solvable. With the right research program, conducted on the right timeline, funded with the seriousness the question deserves, we can know before the first permanent residents arrive whether 0.38 grams is sufficient for healthy human life and development. If it is, if the data shows that Mars gravity is above the physiological threshold for long-term health, then the colonization plans can proceed, with that crucial uncertainty resolved. If it is not, if the data shows that rotating habitats are required for healthy development, then that requirement can be incorporated into the colony architecture from the beginning, rather than retrofitted in crisis. Either answer is useful. Neither answer makes Mars impossible. Both answers make Mars colonization more honest, more grounded in actual knowledge about what the enterprise requires than the current planning, which proceeds on the assumption that the answer is good without having checked. Checking is what science is for. Checking before rather than after is what responsible planning is for. Insisting that the checking happen on a timeline that serves the people who will be most affected, the colonists and their children, is what intellectual and ethical honesty requires. Mars is out there. It has been there for 4.6 billion years, and it will be there for another 5 billion. The extra time needed to answer the gravity question properly is a small investment against that geological backdrop. The first people who go there permanently deserve to go with the best available knowledge, not the most convenient assumptions. That is what taking Mars seriously looks like. Not the courage of going before the question is answered, the courage of insisting the question be answered first. The gravity problem is where that courage is most needed. It is time for the conversation to demand it.